degrees Celsius. But at a higher temperature, it's not boiling temperature. But you have expansion, localized expansion, right? And then you have transport. So if you look at any transport process is a function of temperature. And every complex constituent in concrete responds to temperature differently, right? So you force chlorides through, not just chlorides. Now there is another issue through. Your chlorides, you are applying a potential from one end to the other, a 60-volt potential, to drive the chlorides from upstream to downstream. That's what you're doing. But concrete has this concrete has only chlorides in its pore solution, nothing else. What else do you have? Chloride is going this way. Now, every system wants to be in equilibrium. Nobody wants their equilibrium to be disturbed, right? When you're sleeping, you don't want anybody to disturb you because you were in this wonderful equilibrium. Concrete isn't in equilibrium. When chloride, which is a negative ion, is going this way, some other negative ion says, I have to escape here so that the overall negative ion concentration is the same. And what is that negative ion which you have in concrete? What's the only other negative ion that you have? Hydroxides, right? For every chloride, for charge balance, one hydroxide goes the other way. While you're pushing the chloride, your hydroxides are going the other way. But what are you measuring? In a rapid chloride, what are you measuring? Charge passed. Total charge passed. So the hydroxides doesn't have any charge? Actually, hydroxides have much more electrical charge than chlorides. You're measuring a bunch of hydroxide concentration then. You think somebody told you these are all chlorides, you went in and measured a bunch of hydroxide movement. That's all what you did. And you get, oh, I have 4,000 coulombs. 4,000 coulombs is bad, 3,000 coulombs is okay, lesser than 1,000 coulombs, you're great, wonderful concrete. Right? What have you done? You've basically measured a lot of hydroxide movement. Yeah, chlorides of course went through the other side, but your effective measurement was hydroxides because hydroxides have a higher charge. Right? And then there are positive ions, so we haven't even gotten there. There are sodium and potassium that responds the same way because you have sodium hydro. I have a paper that I did about 5 years ago on the complete theory behind this, and you can download it from my website. Complete theory behind, and then silica fume guys became very angry at me. Well, I didn't explicitly say silica fume, I said some materials, but they figured out what that is. So we haven't talked about positive ions, sodium and potassium, basically, right? Now, for localized charge balance, I'm talking about global charge balance. For localized charge balance, you have positive and negative ions balancing, sodium and chloride. While you are driving these sodium chloride or chloride ions under high speed, under high potential through this, think about a system, and a lot of people do this test on alkali activated concretes and geopolymers. Please don't do it. Okay? That's such a bad test for anything with a higher alkali concentration. Because the moment chlorides go in, and in a system like geopolymers where you have a lot of aluminates, what happens? The chlorides are always very happy to be trapped by aluminates, and you get what is called Friedel salts, chloroaluminates. And then, because chloroaluminates are formed, further chloride transport is harder because chloroaluminates start blocking the pores. And then you say, look, my RCPT value is very low, it's only 1,000. It's 1,000 not because chlorides, not because this is very dense, because you have some local pore blockage where chloroaluminates are formed. So you have so many confounding things in this test. Now, to give you why silica fume does this. Okay? If you measure the pore solution ionic concentration of concrete when you have silica fume, right, you reduce, because you have much higher reactivity of, of course it does some pore refinement. I mean, it's not to say that it's not doing anything. It does some pore refinement, but silica fume lowers the total conductivity of the pore solution. So typically when your pore solution has a conductivity of about 12 Siemens per meter. A Siemens is an inverse of ohm. Okay, ohm is resistance, Siemens is conductance. So Siemens per meter is conductivity. So about 12 Siemens per meter is typically your pore solution conductivity. That is mightily contributed by hydroxides. That 12 Siemens per meter, because hydroxides have a high individual conductivity, much higher than sodium or potassium or chlorides. So this 12 is given by hydroxides. You lower it down to about 10, 9.5 to 10 when you have silica fume, because your silica fume reacts with calcium hydroxide, right? So the hydroxide concentration is effectively dropped. Because the hydroxide concentration is effectively dropped, go back to what I said earlier, what is moving around here? Hydroxides. Because the hydroxide concentration was dropped, there are not enough hydroxides to flow, therefore you will get a lower current. Your lower current is because it lowered the hydroxide concentration, not only because silica fume was great. Okay? So part of it is because silica fume is good. Part of it is because silica fume fills in all these pores. But part of it is because, so all the silica fume companies will come in and say, look, your RCPT is lower by 5 times when you use silica fume. 5% of silica fume, your RCPT drops down by 5%, by 5 times. 3 out of that 5 time drop is because of hydroxide. 2 out of that 5 time drop is because of silica fume's reactivity. So if they come in and say, from 4000 to 1000, silica fume actually, the densification of pore structure gets it down to 2000, and then conductance gets it down to 1000, that's much more reasonable. But when silica fume, oh, it's so well densified that I have a great concrete, is a wrong notion. You can get the effect of silica fume through what is called an ultrafine fly ash. You can ask the fly ash companies, and I've been talking with some of these people to see if they can do it. All they have to do is, above the electrostatic precipitator they are collecting fly ash, they have to install just one more, so that anything below 3 microns they capture. Once you have a material below 3 microns, a good fly ash rich in silica and alumina will do pretty much what silica fume does, because particle sizes, right? Particle size and reactivity, I told you how particle size are influencing reactivity. Remember that, which we did on Monday or Tuesday, one of those days, right? It's exactly the same thing. So when you want to do a permeability measurement, when you want to do an RCPT measurement, be very aware of what you are actually measuring rather than the one number. But again, the downside is, again, something that I told on Monday, the people who are approving this are technocrats who want this, the bureaucrats and not technocrats. The guy who is sitting and approving this and wanting to get this really good mix doesn't know enough about the material that he is getting, so something that apparently looks good is good in their view, and there is nobody to correct it because everybody wants to be safe rather than sorry, right? You want to play safe, you don't want to, I mean, also, I have experiences, right? So when I finished my master's from IIT, I went to work for ISRO in Bangalore, satellite center. We were doing designs at that time. Second launch pad in Sriharikota was being built at that time. So this is huge launch pad, heavily reinforced. I don't remember what the thickness was. So so I sat down, I was just very fresh from college, so excited, got this project. So we sat down, did a lot of designs, and spent sleepless nights because I was a bachelor, didn't have anything to do at that time. So did all these nice designs, and then was so excited. After 2 weeks, went to my boss and said, I did the design. First question, who asked you to do? I said, oh, that's an interesting question, because isn't that government is paying me for? Strange, right? You employ me, I do my job, and you say, who asked you to do it? So I said, fine, sir. I thought, we had so many meetings about this. We are all doing it. So I thought we are doing it. No, L&T is doing the design. So what are we doing? Oh, you just have to sign off on the designs, right? So basically, they'll come with sheets of design. All I had to do is I was a class 1 gazetted officer. I had my green stamp. I had to sign and stamp. I thought it was such a waste of my time just to sign and stamp. And so I told him, and he said at that time, no, you probably wouldn't last here long. I said, yes, I figured it out. He said, he said, no, if you really want to go and do a PhD, you don't want to waste your time here. This is what we do. So I was wondering, how are the satellites going up and staying up in air? Then I figured out, very interesting, and this is, and I think I've talked to a lot of other people in private and public industry in India, and this is my observation. Okay, satellites do stay there. Look, we have some of the best satellites available, right? We have some of the best information satellites. Europeans now want their payload to be in our satellites because our satellites are so reliable and so cheap. We send Mangalyaan at a fraction of cost that NASA, for the cost that NASA spends on wining and dining alone, right? So we do this wonderfully. Why? 90% of the work is done by 10% of the people. And while I was in ISRO, was unfortunate to be in that 90%. 90% of the work is done by 10% of the people. And that 10% is so good that you throw them in any circumstance, they will come out flying. And in ISRO, I've met a couple of people who are just, their dedication levels are just unbelievable. And that's, if we can get that 90-10 ratio to about a 60-40 ratio, we'll become unbeatable. That 90-10 to 60-40, that's it. That's all. I'm not looking at 100% efficiency. You don't need it. If 60% of the people of the workforce does 10% more than what they are expected every time, I think we will be fantastically great. And I've noticed, even in private companies. I work for a private company. I have a lot of friends working in private industry in India. I don't include software in this, okay, so don't get me wrong. For them, it's a different story. Okay, they are in a different planet because I'm talking about people who have job security. Okay, software does it, they'll be fired one day, right? They'll be fired one day, or it's a different world. But if we get to about 60% of our people, or 40% of our people doing work, that'll be phenomenal. Any other questions? Yes.
What would be the effect of waterproof microstructures?
So now I can talk like a waterproofing company representative. I can talk like somebody who has nothing to do with that, and I can give you different answers. If I'm a waterproofing representative, they'll tell you, if you have an integral waterproofing compound, you have IWCs that they sell in boxes, right? That they say, put one box for every bag of cement. Is that how they sell now? That's how they used to sell. Put, what is that called? Dr. Fix-It? So one box. So if you do that, I don't know how it waterproofs, to be frank. They talk about a crystallization that happens inside and then blocks the pores, and crystals block the pore. Maybe that's happening. I haven't really investigated that. And then there are surface applied waterproofing compounds which are just barriers. And barriers work reasonably well until you break the barrier. The integral waterproofing compounds, if they really form the crystal that they say it forms, and they say that under high pH it is stable, but I haven't seen any data to show the long-term stability of their waterproofing crystals at high pH. But I haven't done research on that, so I can't comment on that. But the proof of the pudding is in the eating, right? So if people apply it and it's working, might be okay. But my point is, concrete should not need a waterproofing compound. A well-made concrete should not, it might need an external barrier, an external coat. But if you're like in NIT and you design your structures like this, even if you have an external coat, it's not going to be helpful. But you can have an external coat to be protective. You can have a protective barrier, very similar. I give this example all the time. When it's very cold outside, I don't run in a t-shirt, right? I wear a jacket because I want to protect myself. So if you're putting your concrete in a place that's extremely humid and a lot of moisture, protect it by all means. But then, I don't eat a pill every day because it's cold, right? I don't change my internal structure because it's cold. You don't have to. A well-made concrete, if you follow the processes that we talked about, should not need it. In India and in a lot of developing countries, the problem is that admixtures are treated as the solutions for your construction errors. That has to stop. none of the admixture solves construction workmanship problems. It might mask it in the short term, and it's enough for them for it to mask in the short term because they get their money in the short term. You're not telling them, give me the admixture, let me look at the building performance for 20 years and I'll pay you, right? You're not telling them that. You're telling them, okay, come back after 30 days or 90 days, I'll pay you. Short term it works many of the times, but long term it will not work. You can make a porous concrete with the best possible admixture in the world, it will still corrode the steel inside. You can make a porous concrete and coat the steel with all possible kinds of things. It's enough for that one little crack or opening in the coating so that your entire steel gets corroded later on. So none of these will solve any of your problems. We think it solves because in the short term, it masks these problems. So good concrete will not need waterproofing. Bad concrete waterproofing might be okay because it masks some of these effects.
If there is surface coating, what will be the effect of hydration process?
Okay, so there are a lot of times, so even in the US, and a lot of times when you do bridges and all, bridges and pavements, they apply a curing compound on the top. And India also, I think you have a lot of curing compounds. The basic idea is, if you have a 0.4 water cement ratio concrete, like I showed you initially to start with, right? For the cement particle, you have given it an ocean with 0.4. So if you have a 0.4 water cement ratio concrete, and if you do the curing compound application as soon as the final set is done, you have trapped enough water in the system for it to hydrate. You don't have to give external water. You have enough water in the system because all the curing compound does is to prevent evaporation. Curing compound is an evaporative barrier, it's a water barrier. It just prevents evaporation from happening. So you have enough water in the system to hydrate. Your waterproofing compound also does the same thing. It will keep the water within and you can hydrate. And then like I said, do you really want your entire cement to hydrate? No. So it used to be when houses were being built, people said, oh, cure for 14 days, right? You put in a roof slab and cure. Nowadays, do you cure for 14 days? Maybe for 7 days because you don't have enough time, you have to do construction fast. You don't really have to. If you do a curing compound is as good as curing, as long as you can't do a 0.3 water cement ratio concrete and expect it to be self-cured. You have to apply external water. But at 0.4, theoretically, remember I showed you the calculations. You need only 0.32 to completely hydrate, theoretically. But that doesn't happen also.
Mostly in developed countries, precast is the compounds that are used. How is curing different from cast?
No, we do a lot of cast in situ. Every pavement, again, maximum amount of concrete that's used in the US is for pavements. Every pavement is cast in situ only. Miles and miles and miles of concrete pavement cast in situ. No, pavements, roads. Miles and miles and miles and miles of roads cast in situ. Precast is used only for, we'll do a little bit of precast for bridges, bridge segments, box girder beams, all are precast. And then for warehouses, use precast slab for warehouses. Floor slabs are cast in situ and walls are typically precast. High-rise buildings you sometimes use precast. If you're using precast, they typically use a temperature of about 60 to 70 degrees Celsius, which means they are accelerating the hydration of what should happen in 28 days in about 6 hours. Then you don't need curing for hydration because you've gotten the strength that you want. You will still apply some kind of a compound outside or might cure it a little just to control cracking. That's it. You don't need any more curing in those circumstances. Okay. Yes. Yeah. Okay. So if you do ASTM 1585, that's a standard force optivity test. It's a very good test for a number of different reasons. You put concrete, you seal all the sides, you expose just one surface and you put in a little bit of water so that you have capillary action coming in, right? That is a standard action through which water gets into concrete. That's exactly the action through which water gets into concrete. So you have the surface pores that gets filled in very fast. That is why you get a very quick initial curve. The first few hours, in 6 hours or so, you get a curve like this. You call it the initial sorptivity. And then the curve starts to flatten out. That's a secondary sorptivity. The first few, 2, 3, 4 millimeters deep, depending on what is the surface nature of your concrete, that is your initial sorption. That is how water goes in first. The advantage of this test is, this is, like I said, this is exactly how water goes into concrete. And the initial sorptivity is a very good test because it tells you the quality of your cover layer. And cover layer is the most important layer for concrete durability if you have reinforced concrete. And cover layer is the layer that you completely ignore in your structural design, right? You don't even want to think about the cover layer in your structural design. Whereas for concrete durability, that is the most important layer. So sorptivity test really gives you wonderful information about that, the transport through that layer.
What other durability tests are important?
Depends on what kind of durability concern you have. If you have corrosion, if you're basically worried about corrosion, rapid chloride permeability test is what people typically use for corrosion, but like I said, you're just measuring how fast the hydroxides run around. The other test, which is very similar to RCPT, you can use it with the exact same test method as RCPT, is what is called the rapid migration test, or the non-steady state migration test. ASTM doesn't have a standard for it, but AASHTO, which is the American Association for State Highway and Transportation Officials, they have a standard for it. ASTM hasn't come up with it. Nordic, there is a Nordic standard for it, which even AASHTO has based on for Nordic countries, Finland, Iceland, Finland, Norway, all of those countries. They have a test for it. So this test is very similar to RCPT. The concentration of sodium chloride and sodium hydroxide are different, and the voltage that you pass through is based on how dense your initial concrete is. So you measure the initial current, and based on initial current, you find out what voltage you have to use, and that voltage is typically 20 or 30 volts, not 60 volts, which means the heating component is much lower. Because the heating is much lower, hydroxides don't have the tendency to run around so fast, right? It will still account for some hydroxide effect like you see, but you are never mentioning the total charge passed, but you measure the actual non-steady state diffusion coefficient. So using temperature, you measure the actual temperature, using the molar gas constant, using the applied voltage, and using the concentrations, you measure a diffusion coefficient. So you basically say that, or a migration coefficient, you say that my migration coefficient is so and so. It becomes a very good test to compare between different things. So I've stopped using RCPT unless the Department of Transportation wants it specifically for some test. It's so easy to do, but I don't trust RCPT for any useful quantification. Yes, I can talk to you about something about life, but life prediction is an entire topic in itself. So I'll tell you what is that software called? Life 365. Okay, so freely available. Only one problem with Life 365. Silica Fume Association made that software. So it has some little bias because there's a lot of input parameters. So if you see Life 365, you will see SFA right on top of it. Okay, but it's a good software. You can use Life 365. You can give the geometry of your structure. You can give your reinforcement. You can give your concrete parameters. You can put in whether you have surface coatings. You can put what kind of coating. You can put in the effect of fly ash, slag, silica fume, all of that. and then you can find out what is the initiation propagation period. It will allow you to compare different what if scenarios. What if I change the concrete gray to something else, but I put in a bigger coating. All those different things you can do. It will give you a cost analysis. It will give you which is the most sustainable life cycle option. It's a good software to have a first estimate. Again, it's a good teaching software. If you're teaching a class on life cycle analysis corrosion, it's a very good one because students can read the manual for 2 hours and completely do a good project on it. It's a good software. They get exposed to all those different things. But again, the idea is that they also expect concrete to have a certain, so the errors in construction, for example,